Okay, in this example, we're going to do a full projectile motion problem. A soccer ball is kicked with an initial velocity of 15.7 meters per second and an angle of 38.0 degrees above the horizontal. A, find how high the ball flew, and B, what is the ball's range? Range is just the total displacement, which ends up being the horizontal displacement of the projectile. So the first thing I'm going to do is I'm going to draw my picture. So I want to make sure that I have my picture. Let's go ahead and draw the projectile. There we go. And I'm going to label this as my 0, 0 point. And I'm going to go ahead and draw my velocity. And we want to make sure that that's red. Oops, I'm a little bit off. So I'm going to, there we go. And so there you go. There's your picture. Let me go ahead and write the initial velocity. You can write V0, V sub 0, or V sub I. Either one is fine. Okay, now what I'm going to do is I'm going to write my components for my each variable. Okay, this gets a little bit tricky now because we have a full projectile. And that means that we have to make sure that if there's an angle given, that we're actually using that angle. Okay, if they give you an angle and you are not using your sine and cosine, there's something wrong. Okay, you have to use sine and cosine to break your vector into components, the x piece and the y piece. Okay, so let's go ahead and do that. We're going to go ahead and write out our initial my initial position first. Let's do that. So my initial position, that's easy. The ball starts at the origin. So 0 meters I hat plus 0 meters j hat. Okay, next my final position. Well, if I go all the way to the end, which is right here, I'm at some distance d sub x away, so that's a question mark. I don't know how far away I am, but I do know that my final position is also 0 meters per second. I mean 0 meters j hat. Okay, my initial velocity, it's a vector quantity here, and it's at an angle. So what I'm going to do is I'm going to go ahead and draw out the components on the drawing so that you can see how I'm breaking this into components. Okay, so the first thing I'm going to do, actually let me get my arrow, it's easier this way. Here's my x component, here's my y component. Okay, all I have to do is slide this y component over, and notice that I make myself a right triangle. Okay, the angle here is the angle theta. Okay, for a right triangle, it's opposite over hypotenuse, and that's sine. Okay, let me do that again. Opposite over the hypotenuse, and that's equal to sine theta. Okay, so what we're going to do is write that out. Sine theta is equal to the opposite side. Now this is going to be Vy. So it's going to be Vy over V. If I multiply both sides by V, I end up with Vy is equal to V sine theta. Okay, so that means my y component is sine theta. Now let's look at the other one. Okay, adjacent here over the hypotenuse is cosine theta. Okay, so adjacent side over the hypotenuse is cosine. So let's write that out. Cosine theta is equal to the adjacent side. Well, this adjacent side right here is just Vx. Okay, so it's going to be Vx Sorry, I'm really trying to do this well with my finger. Vx over V. Multiplying both sides by V, I end up with Vx is equal to V cosine theta. Okay? So, all I'm going to do now is I'm going to substitute the numbers into my calculator in order to solve for Vx and Vy. So let's move this over to here. Okay, so V is going to be the 15.7 meters per second, and we're going to multiply that by the cosine of 38. So I'm going to take 38, take the cosine of that, and then I'm going to multiply by the 15.7. Okay, and that gives me 12.3. So my x component here is going to be 12. Let's round that up to 12.4 meters per second I hat. Now let's solve for the y component. Remember, the y component is down here. It's right here. And it's going to be equal to the 15.7 times the cosine of the angle 38 degrees. So what I'm going to do is I'm going to put 38 sine. And that gives me 9.67. Oh, that's big. Okay, so that gives me 9.67 meters per second J hat. If you get a different answer than me for this, please write it down in your notebook. I'm using a computer calculator. I'm not sure that it's in degree mode. It could be that it's preset for radian mode, or it could be that I'm doing something wrong with the numbers as I put them in. Okay, so please make sure you check my numbers and make sure they're correct. Okay, for V final, this is still 12.4 meters per second I hat. But here's the thing about a projectile motion. Remember when I told you in free fall that the velocity it goes up is equal to the velocity it comes down with at the same position? Well, that's the same thing here. So this is going to be negative 9.67 meters per second J hat. Okay? So as it goes up and as it comes down, you get the same values. Now, your acceleration is the same as always. It's going to be 0 meters per second squared I hat minus 9.8 meters per second squared J hat. That's a constant. You never have to forget about that. I mean, you never have to worry about that one. Okay, that's always a constant. Okay, now what I've done is I've made my boxes bigger, but I've put them one underneath the other so that I can actually write in the box without it making a mess. Okay, so what we're going to do is we're going to take all of our information right here. Okay, right here, this is all your I stuff. Okay, and this is all your J stuff. So I'm going to take all the I's and put them in the I box, and I'm going to take all the J's and put them in the J box. Okay? So let's go ahead and do that. So the first box is 0. This is X. Oops, now I'm making boxes. Okay, so this is the X direction. Okay, so I'm going to have D initial, D final, V initial, V final, A, and T. My initial position is 0. My final position is unknown. The initial velocity is given. It is 12.4 meters per second. So this is 12.4 meters per second I hat. This is 12.4 meters per second I hat. This is 0 meters per second squared I hat. And the time is unknown. We don't know how much time it is. But remember, whenever you don't have the position here and you have no time here, you must solve for time. You got to have both. in your equation, or you will get 0 equals 0 every single time. So make sure that you solve for time. Okay, so I'm kind of done with this for right now. Now I got to move to the y boxes. What I'm going to do is I'm going to give myself a lot more room to solve a problem up here. Okay, so I'm going to give myself some room, and I'm going to go ahead and put my boxes down here. Okay, so I have D initial for the y direction, D final, V initial, V final, G, and T. This is negative 9.8 meters per second squared J hat. Time, we're going to have to solve for it. Final velocity, initial velocity. Well, let's see here. My initial velocity is 9.67. I'm going to put 9.67 meters per second J hat. This is negative 9.67 meters per second J hat. My initial position is 0 meters J hat. My final position is 0 meters J hat. Okay, there's several things that I can do to solve for time. Okay, I can go ahead and solve for V final minus V initial equals AT. I can solve for delta D equals VIT plus 1/2 GT squared. I can pretty much do anything I want to do to solve for the total time. I'm going to go ahead and use V final minus V initial equals GT. So V final minus V initial equals GT. Okay. Now let me explain something else about these problems. I really want you to be careful. Notice that I have the y up here. Okay. You really have to be careful and make sure you're not using x equations in y and y equations in x. Okay, so if you're solving for the vertical direction, you need to make sure you're using the numbers in the y boxes, not the x boxes. That's why I really, really want you to use these unit vectors so you know the direction. Okay, 9.8 meters per second squared south never goes in the x direction. You cannot use it when solving in the x direction. Okay, really important. Okay, so I'm going to go ahead and divide both sides by g to solve for t. So my time is equal to v final minus v initial over g, which is equal to negative 9.67 meters per second j hat minus 9.67 meters per second j hat. Sorry, that looks horrible, doesn't it? Oops, let me get my eraser. Let me fix that for you. Meters per second j hat. There you go. All divided by negative 9.8 meters per second squared j hat. Okay, all the j hats are going to cancel out. Let's go ahead and put this in the calculator. Oh, I want that smaller. There we go. Okay, so I'm going to take 9.67 negative minus 9.67, and then I'm going to divide that by 9.8. Make sure you have the negative, and I get 1.97 seconds. And that's what I want. Well, wait a minute. 19.67 minus 9.67, that's actually going to give me 4 significant digits. So I actually need to make this 1.973. Remember, when you're adding and subtracting, it's the precision that you worry about, not what's in front of the decimal point, but what's behind it. There's 2 digits behind the decimal place. That means my answer has to have 2 digits behind the decimal place. Okay, so you got to be careful when it comes to significant digits. I know it's crazy. So my time is going to be 1.973. And it's only this number because I'm dividing by 9.8, which is a constant. So I ended up with 4 sig figs. I got to end with, in the numerator, I got to have 4 sig figs when I end. Okay, so this is the time I'm going to use in the x direction, and it's 1.973. 1.973 seconds. Okay, so now I can solve for my range or my total displacement in the x direction. I'm going to go ahead and use another formula, okay, just to show you can use many different, I mean, there's 2 different formulas you can use here. So I'm going to use delta D is equal to 1/2 times V initial plus V final times T. Okay, so delta D is equal to 1/2 times 12.4 meters per second I hat plus 12.4 meters per second I hat times 1.973 seconds. Now, some of you may have already noticed and said, well, wait a minute, 12.4 plus 12.4 is 2 times 12.4, and 2 divided by 2 is 1, and that would be correct. But we're going to write this all out anyway. So this gives me 1/2 times, let's see, 24.8 meters per second I hat times 1.973 seconds. And we're going to go ahead and calculate that. I'm going to take 1.973 and multiply that by 24.8. And then I'm going to divide by 2. And that ends up giving me, I need 3 significant digits because I'm multiplying and dividing. So it's going to be 24.5 meters I hat. I got to move this all over because I don't have enough room. Okay, so there's my total range, 24.5 meters. Okay, I'm not done though, right? I know you're thinking, oh my God, we're not done yet. No, we're not done. We figured out the range, but we haven't figured out how high the ball flies. There's a reason why I've waited until now to do this. In order to figure out how high the ball flies, I have to go from the middle point straight up. Okay, that's the halfway point. Okay, it takes half of the time to get to that position. Okay, it's half of the total range. So for instance, we've traveled 24.5 meters for the full movement of the ball, but half of that would be how far we go in order to get to the highest point. So what we're going to do is we're going to set up another set of boxes for the y direction. So let's go ahead and do that here. And I'm going to cheat a little bit because that's the wonderful world of computer animation. If you need to pause at this point in order to write out your boxes, please do so. I'm going to go ahead and continue on with the problem. So now I have my initial position halfway, my final position halfway, my initial velocity halfway. It's actually the halfway velocity. My final velocity halfway, g, and my time halfway. I put the halfway just to make sure I remember that I'm only going halfway. Okay, now there's some tricks here. My initial position is still 0 meters j hat. G is a constant. It's still 9.8 meters per second squared j hat. My time is just going to be 1.973 seconds divided by 2. That's halfway. Now, what's the velocity in the y direction at this very top point? Remember, the y direction motion is going straight up and straight down. Yeah, it's going to be 0 for the final velocity. So, for a halfway problem, this is going to be 0 meters per second j hat. Now, what is my initial velocity for the halfway problem? It's still going to be the same as this number here, the 9.67. So it's 9.67 meters per second j hat. Okay? What do we want? We want this number right here. One of these numbers I don't have to use. So you want to go as simple as possible. So you want to stay away from the quadratic, which is delta D equals VIT plus 1/2 AT squared. Stay away from that one. You also want to stay away from the V squared final minus the V initial squared over 2A delta D. Stay away from any squares as much as possible. So what I'm going to do is I'm going to go ahead and cover up the acceleration, the g, and I end up with delta D is equal to 1/2 times V initial 1/2 plus V final at the 1/2 all times T the 1/2. And this is my height halfway. Okay, so my halfway height is going to end up being 1/2 times my initial velocity, which is 9.67 meters per second j hat, plus 0 meters per second j hat, all times 1.973 seconds divided by 2. Okay, so we're going to go ahead and plug that into the calculator. And we end up with 0.5 times 9.67. And then I'm going to go ahead, I'm going to move this over so I can see it, times parenthesis 1.973 divided by 2. And that gives me 4.77 if I use 3 sig figs, which is exactly what I need, 3 sig figs. So that's going to be, again, 4.77 meters j hat. So it reaches a height of 4.77 meters. Okay, so let's go ahead and recap here on the full projectile problem. The first thing you need to do, draw a picture. Second thing you need to do, draw your reference point. In this problem, it's 0, 0. Okay? Let me go ahead and change this so I can show you my magic pen. This is actually kind of cool. Okay, so 0, 0. Actually, there you go. Okay, draw your reference point. Now it won't go away. Oh, great, I've broke it. Okay, well, I'm just going to continue talking, and hopefully this will catch up. Okay, next thing you do, break your initial velocity into components. It's actually the only thing that needs to be broken into components using sine and cosine. Next thing you need to do, write your vectors out in component form. Next thing, substitute into the boxes. Remember, for a full projectile problem, your initial and final position in y is 0. Your initial velocity and your final velocity are the same magnitude but opposite directions in the y direction. In the x direction, your velocity remains the same. Okay? Next, for a halfway, where you're finding the height of the problem, you're going to use half of the time and solve it as if you're looking for your y position. Okay, again, if you have any questions about this problem, just go ahead and make a note and let me know next class. There we go. I had to kick myself out.